Hi everyone. Just going to talk through these slides. The question is, what is calculus? What is Math 150? Calculus, it is just way above and beyond anything that we have seen or dealt with before. And that's a big reason why you can't hide behind formulas and procedures. You really have to know exactly what you're doing in order to even pass, let alone do well. I'd really like to share just what is the big picture? What is this course all about? What is calculus at the end of the day? And then some details just to give you an overview of what this is. Well, the word calculus comes from calculate, but that's not what we mean. It has a very specific meaning when we take when we take the course. So when we say calculus, and let's see here there we go. Okay. It's the study of change at a given moment. Okay, so back in pre-calculus and in algebra, we studied change, maybe like average velocity might have come up, maybe. We mean beyond that, the study of change at a given moment or given instant. So what's happening to an object, or maybe not even an object, maybe just some kind of an event as it's changing in the given instant. So I found this picture of this flower blossoming. So, that's the same flower, growing, and we see a snapshot at all these different moments. Okay, so more on this as we move along these slides. The course that we call calculus, it's really short for infinitesimal calculus. Okay, the infinitesimal is the infinitely small. So in order to study change at a given instant, it's like we have to divide time over and over and over again until we get an infinitely tiny little slice of time that we call an infinitesimal. And so the picture I found, you see that number line, and the number 3 is highlighted, and then we're zooming in on the number 3. But what do we find when we zoom in on 3? There's not less numbers. We see it's packed with even more numbers, and so we're dividing it and magnifying it down, zooming in, and we're going to keep zooming, if you will, until we get to the infinitely small, the infinitesimal, just an instant in time or on that number line. Okay, moving on. Maybe before we get into the details of the course anymore, we talk about the usefulness. How is calculus useful? Okay, well, we're going to study change and velocity and that sort of thing, but it goes way beyond that. So here, I'm just going to give a list of some of the applications, and we're definitely not going to do all of these in this course. But the more calculus courses you take, and then some of you guys, you're going to study physics or engineering or even economics, chemistry. I mean, all these things are going to involve calculus, as you go. Obviously, this class is required, so that makes sense. It's to model and predict behavior for objects in motion. That's a big one. We do that one a lot because that's kind of an easy one to grab. And that's even what the picture there is on the right. You see some kids jumping around in a trampoline park, so they're all in motion. We took like this snapshot in time. Some of them, when this picture was taken, are moving very quickly. You see the guy, the kid in the lower right, he's doing a backflip at the moment the picture is taken. So he's actually traveling very fast, spinning. Some other people are probably, pretty still. So you see a guy there with yellow, on his shorts and a sweatshirt there, kind of in the middle. So it looks like he's at the top of his jump. He's sort of just suspended, and he comes in. There's no blurriness to him. And I think the guy just to his left, that's way up, is probably about at the top of his jump. Then, of course, there's a younger kid who's standing on the trampoline. And so maybe they aren't moving so fast, although they're still in motion for sure. Okay, anyway, some other things. Population growth, we're going to study that a little bit. Cooling and warming objects as something's warming up or cooling off. Optimization, okay, we can optimize things. Just kind of throw that out there. It'll come back later at a few chapters down the road. Chemical reactions. There's a chemistry roller coaster design. There's an engineering application, water flow. And then the last two are actually a little bit different. Distance traveled and volumes of curved spaces. And those we are looking at calculus in a different way than the others. But I won't go into that now. Okay, here are a couple of examples. Obviously, we're going to see some applications. The majority of the things that we cover is just learning calculus, but we're definitely going to get our word problems and our applications thrown in for sure. So our first example, this is a problem that we'll see much further into the course, and it's pretty interesting. A Ferris wheel has a radius of 10 meters. This is a pretty large Ferris wheel. Maybe you would find at the fair or out on a pier or something. Radius 10 meters and rotates at a rate of 1 revolution every 2 minutes. Okay, so the people get a nice ride. They're not going too fast there out on the edge of that circle. How fast is a rider rising when he or she is 16 meters above the ground? So if you kind of picture that, and I kind of wish I had maybe a board to draw on, but if you imagine a Ferris wheel, just the circle of the Ferris wheel, if someone is 16 meters up, or maybe if their car, their little basket that they're riding in is 16 meters up, so they're above the halfway point, right? So the halfway point would be 10 meters, and they're going to get all the way up to 20 meters at the very top. So at 16 meters, and maybe imagine they're still rising, how fast are they rising at that moment? So, we know how fast this thing is spinning. As they're going up, they're rising vertically, but they're also moving horizontally when they're 16 meters up. So how fast are they rising, which we would just think is vertical, at that given instant? So that's kind of the sensation you feel. I know when I'm on a Ferris wheel, it always feels like I'm moving faster when I'm, moving more vertically than horizontally. When you're at the edges, if you think of left and right, it feels like you're moving a lot faster when you're moving vertically. And then you get to the top and it almost feels like it's slowed down, even though you're moving just as fast. It's just more of a horizontal. Anyway, that's a pretty cool application. Watch for that later on in homework. And here's another one, very different. A sphere of radius 2 inches has a hole bored through the center of radius 1 inch. And so I found this picture of some beads. Looks like they're made of wood and they've had a hole drilled down the middle. So a shape like that. It's got a radius 2 inches and then there's this hole of a radius 1 inch down the middle. Can we find the volume of the remaining portion of the sphere? And using calculus, we're able to do that. And you might think, oh, no big deal. It's like a cylinder has been drilled out through the middle. So can't you just take the sphere minus the cylinder? And no, because it's not a cylinder. The edges are rounded. The very ends, it's not a flat cylinder at the top and the bottom. It's rounded off. So a much faster and a better way, a more efficient way to get that volume would to be using some calculus techniques. Okay, so this really hints at these two branches of calculus, and that's like, the Ferris wheel problem would be one branch, the sphere with the hole drilled out is another branch. Those applications from a few minutes ago, all of them, most of them were one style, and then those last two I said were different. So these are the two branches that we study. They're called differential calculus and integral calculus. We spend most of our time, 3/4 of our course will be on differential calculus, and that last 1/4 is integral calculus. We certainly don't do everything there is to integral calculus or differential calculus in this course. But the reason why only 1/4 integral calculus, we just run out of time. So the semester ends, or the term ends, and calculus 2 picks up right where calc 1 left off. And you begin calc 2 looking at integral calculus, and you go further, and then you go back and look at differential calculus a different way, and you kind of there's definitely a lot of common ground between them, that knowing one will help you with the other. Okay, but just what I want you guys to take away, there's these two branches. Most of our time is devoted to differential, and then that last quarter, which for us is like the last week and a half or something, is devoted to integral calculus. Let's talk just a little bit about each one. Differential calculus, that's kind of what we were getting at earlier, the instantaneous rate of change, the study of change at any given moment. We're going to use this word derivative. You're going to hear that word again and again and again, probably 10,000 times in the next few weeks. You're going to hear the word derivative. What does that mean? So, well, it's an instantaneous rate of change at any given moment or instant. Graphically, this is big. It's good to see this now. Graphically, it's the slope of a tangent line to the curve. So I'm hoping my mouse will come up on this video here. So I've got this curve f of x in blue, and if I want to know how fast my function is changing at a given instant, say this instant right here where this dot is, I would draw this tangent line, we call it, in red. It moves in the same direction as the curve, just grazes by. It's actually, and it's the slope of that line, is what it says up here. The slope of that tangent line is how fast my curve is moving at that instant. Just a word on integral calculus. What is this? And it's completely different. We're not talking about instantaneous rate of change here. We're talking about net change. It's the net change of some quantity. And even integral is actually shortening it. It's the definite integral is the more technical word for it. The net change of a quantity. Okay, well, I won't get into it. Really, what I want you to take away is this shape with this graphed area here, that shaded area. It's graphically, it's represented by the area between a function and the x-axis, with a starting point and ending point from A to B. We will be able to find areas such as this between the x-axis and some function up above it. We'll be able to find that area exactly. And you're like, that's such a weird area. It's curved. How can we find that exactly? That is the power of calculus. And we can even go from areas, curved areas, to curved volumes, which is what those spheres were about. Okay, moving on. So it turns out that differential calculus and integral calculus are very closely connected by this thing called the fundamental theorem of calculus. The fundamental theorem of calculus, that's a big deal. We learn about it right before we get into integrals. So we're going to learn all about differential calculus. And then just as we learn about integrals, starting in that last quarter, we learn the fundamental theorem of calculus, and it combines the two together. We'll see their relationship. It turns out the techniques to do differential calculus, if you do them in reverse, you're doing integral calculus. But for now, I just want you guys to know these are opposites of one another, and that just blew everybody away. The slope of a tangent line is connected to those curved areas. Who would think that? And it turns out they're opposites. So cool. Okay, wanted to finish up really fast. What are the goals of this course? To develop the concept of the infinitesimal, the derivative, and the integral. We will perform derivatives and integrals on all basic functions, and we'll see some applications. And I'll just end with this. I found this image on Google. A goal without a plan is just a wish. We've got a goal and a plan. That's all for this video.